My name is Giulia Galli. I'm a professor at the University of Chicago in the Pritzker School of Molecular Engineering and the Department of Chemistry, and a senior scientist at Oregon National Lab, where I'm the director of the Midwest Integrated Center for Computational Materials. And it's my great pleasure to introduce the moderator of today's session, Mandy Birch. She's the CEO and founder of TreQ, and an open architecture quantum system engineering company expediting next generation computing cluster. She is a global executive engineer with decades of experience in national security and quantum computing, and she has led teams with more than 50,000 people, brokered over 600 complex multi-sector partnerships, and of course demonstrated agility between startup and larger enterprises. Mandy also helped drive a quantum computing company from its early stages through a successful IPO. She holds degrees from US Air Force Academy, MIT, and the Fletcher School of Law and Diplomacy. Mandy.
Thank you so much for that kind introduction. Do we have anyone here in the audience today who went into a fab in the 1970s? Anyone? 1970s? Well, if you had, you might remember the smell, the ozone, the metal, and the warm silicon. Those early engineers were building bridges between the analog and digital worlds, transistor by transistor. And at the time, every company built everything on their own. They built the chips, the memory, the software, the packaging. The integration work was really a heroic artisanal craft. And over decades, that began to change. Interfaces emerged, supply chains grew, and open architectures sparked the emergence of a global ecosystem, with each layer becoming more and more specialized, interoperable, and scalable. Quantum is now standing at a similar threshold today. We're back in the business of creating new fabs and manufacturing processes, figuring out how to build and connect components and devices built on fundamentally different physics. And in the next few years, we'll begin to transition from this artisanal to interoperable ecosystem. And to discuss this transition and the challenges associated with it, I'm delighted to invite our three panelists, colleagues working on quite different technologies to join me today to discuss this transition. So first we have Kristen Pudenz at Atom Computing. Dr. Pudenz leads research programs at Atom Computing. She brings over a decade of experience in translating quantum information science into applications for industry and government. Atom builds highly scalable gate-based quantum computers using optically trapped neutral atoms, and that's an architecture that's proving both elegant and powerful. Kristen's background bridges theory, experiment, and mission impact, so she knows what it takes to turn scientific possibility into interoperable systems. So welcome, Kristen. We also have Johannes Pollen. He's at EeroQ and Michigan State University. Dr. Pollen is co-founder and chief scientific officer of EeroQ and professor at Michigan State University, where he holds the Cowan Distinguished Chair in Experimental Physics. His team is pioneering a quantum computing platform based on electron spins trapped on superfluid helium, a beautifully delicate system with some surprising strengths. Johannes also leads the Laboratory for Hybrid Quantum Systems, where he explores how combining different quantum materials and modalities might create new capabilities none could achieve alone. Welcome, Johannes. And I'd also like to welcome Dr. Lorenzo Martinelli at D-Wave. Lorenzo is the Chief Revenue Officer at D-Wave, and his background is deep in enterprise software and optimization. He's led companies from 0 to hundreds of millions in annual recurring revenue. D-Wave is already delivering production-grade quantum systems for optimization problems with both cloud and on-prem deployments worldwide. Lorenzo brings the perspective of quantum that's already out of the lab and starting to solve real customer problems today. So welcome Lorenzo, please, to the stage. Okay, and as we get started, I want to draw your attention to the app where you can go ahead and put questions in at any time, and we'll take a few pauses throughout the session to look at the Q&A that have been put in the app. But to start out here, I'd love for each of you, you're each working on very different computing platforms. Could you just give us a quick introduction to your particular platform and why you think that your particular platform will have enduring value moving over the next 5 to 10 years? Kristen, can we start with you?
Sure. Let's see. Oh, yep. Okay. So Atom Computing is a neutral atom quantum hardware company. So we build quantum computers out of atoms. A really complicated name, I know. What we're doing in the lab is we're taking a laser beam, we're splitting it into over 1,000 pieces, focusing them all down on the common plane, and parking an atom within the potential well created by each of these laser tweezers, right? And so then we can drag and drop the atoms. We get a perfect lattice, and then we can sit out of plane. We can see all the atoms, and we shine other lasers at them to actuate gates and control and do cooling and all the things you need to do really diverse quantum computing operations and make a full gate model machine. And I think the thing that inspires me most about this platform is the potential to scale. We've already demonstrated a 1,225 qubit array, and we're pushing toward the future. We are looking at not only large numbers of qubits, but error-corrected operations, and you can read all about this in the literature, right? We publish our technical progress. So when you're thinking about, optical control, when you're thinking about large numbers of qubits within a single module, when you're thinking about things that can be sort of scalably parallelized across arrays of qubits, neutral atoms are really strong for that. And I'm excited to see where it goes and how atom computing develops it over the next few years. I think we've got a lot to offer.
Fantastic. Thank you, Kristen. How about you, Johannes?
Yeah, can you hear me? Great. Yeah, so as Mandy said, I'm Johannes Pollen. I'm the Chief Science Officer at EeroQ, which is a quantum computing startup here in Chicago. We have a 10,000 square foot engineering facility out in Humboldt Park. So the qubits in our system that we're developing are the spins of individual electrons that we trap above the surface of superfluid helium. It's an exotic, that sounds exotic, but it's actually the system itself has been known to, people have worked on it in various experimental ways since the 1960s. So we do kind of two things to bring this new qubit and quantum computing technology to fruition. We build bespoke quantum measurement devices in-house. We use the Pritzker NanoFab on the University of Chicago's campus. Our engineers work out there to make our spin readout devices that we're developing. And then we work in collaboration with a commercial CMOS foundry to build our underlying scaling architecture. So we've demonstrated recently the very first quantum measurement of these single electron, in fact, the charged qubit states. We're working our way up to the spin. And on the scaling side, we also really like the scaling benefits of these electrons. We've built and tested a 2,500-ish electron scaling architecture on a CMOS chip that's about 5 millimeters on a side and has 30 wires going to it. And we can move the electrons around in concert on that using just a very small number of control lines. A big part of our thesis in quantum computing is that we need to build off of known scaling technologies. Our system works well with CMOS-based manufacturing, and in fact, it's one of the only thing that humanity has ever been able to make at the 10 to the 10 level. And so we want to build off of that classical scaling architecture to really to drive this technology forward.
Thank you. And Lorenzo, you're at the first quantum computing company to be commercial and deliver systems. So
Yep.
tell us a little bit about D-Wave, your platform, and how you see that enduring over
Yeah.
the next 5 to 10 years.
Yeah, also I'll give you more of a commercial view here. So the technology is superconductive in general, and we have very much the same belief of taking advantage of commercial, CMOS technology. So in that world is kind of where also IBM and Google are. The one difference we had is that when we started 25 years ago, believe it or not, the reason why we're there because we've been around that long, gate was really, really far away. So we decided not to just do gate because 25 years ago the road was too long. So we're the only company that are both doing two modalities. One is annealing and one is gate. The reason why that decision was made well before I joined is because annealing is much easier to scale and doesn't have the issues around error correction. So we could get to something that was commercially available quicker and deal with the other things that you need to provide a commercial system. So right now, I think we have 5,000 qubits on the annealing side, which is probably the largest around. And our next stage, we have a pretty defined plan that's been public about getting to over 100,000 by going to a multi-chip environment. We figure out to do multi-chip and maintain the superconductive issues and so on. On the gate side, we're kind of like everybody else is. So obviously, we think it's going to take a while longer before that side gets to a production capability, meaning A, you can solve real problems, and B, you can do it with the stability you need for production. Now, to get to production, that's not the only thing we provide. We had to develop what we called kind of a quantum cloud offering to get people to actually use it. Because yes, for people in the lab, like who work directly with a machine, the rest of the world doesn't want to deal with that. So we have a thing called Leap, which is basically a quantum platform that people can deal with things that are, you don't have to be a quantum physicist to operate it. If you know Python and you know your domain area, you can take advantage of that. APIs, all the things you need. And between that Leap layer and the quantum system, we have to figure out how to make it production ready. What does that mean? Well, if you run something production, you need at least 99.9% uptime, you need sub-second response, and all the things you need that you get automatically when you go to conventional computing, and we have to provide that too. We've had customers now in production for over 3 years. The other thing we had to do, and it's a topic that will come up, is that you can only run certain jobs, or it makes sense to run only certain jobs on a quantum computer, but to solve a real problem, you need also other things. And so, we have another layer on top, which we call it hybrid solver, but basically a software layer that is smart enough to figure out what portion of a task should be run on a QPU versus a GPU versus CPU to get a real problem. And a real problem, I'm talking about things like, workflow scheduling or production scheduling or something like that. So in a sense, I view 3 layers there. And the bottom layer, obviously, a 2 modality, one that it's available now in production and one that hopefully will be soon. I like to make it available soon, but that's not my decision. Anyway, that's us.
Okay, thank you. You brought up a lot of topics we're going to talk about here:
Yep.
interoperability, manufacturing, supply chain, error correction. We're going to get to all of these topics. But before we move on, so you've all each given us an overview of the platform and how it's going to become important in the future. Could we just drill down on that second part a little bit more? I'd love to hear more about, I think there's a hypothesis that in the next 5 to 10 years, there will not just become one qubit type that's relevant. We're probably going to have a future over the next decade that remains multimodal. Do you see any specialty niche emerging for your particular technology? Is there a certain type of problem, for instance, that your platform might be better suited than others, or certain applications that you see as most promising on your platform right now? Anyone?
Sure, I can go again. Atom computing is really focused on building a large-scale general-purpose gate model quantum computer, and that is a sufficient challenge for us. It's hard enough to make this all work at the fidelities that we need, and so atoms like to talk to photons. There is potential to interconnect our systems with other types of systems. I think quantum networking is a rich and deep topic, right? Because each quantum qubit technology can communicate with the outside world, theoretically. Each qubit technology likes to emit a different type of signal, different wavelength. You know, superconducting systems like to talk to microwaves, neutral atoms like to talk to visible. I don't even know what Johannes' system likes to talk to, right? So there's a lot of subtlety and complexity within the network, and we leave that to others, but we could certainly support and be part of a networked quantum infrastructure in the long term. Specifically for atom computing, I think there's two main challenges that are closely interrelated in the cycle within the next 5 years. One is scaling, and I talked a little bit about scaling already, but the second is scaling to support error correction, right? And this is one of my favorite pet topics. I actually cut my teeth doing error correction on the very first D-Wave processor, and now I'm doing all kinds of different things. But the flexibility that neutral atom platforms brings is really promising, and just the point at which we sit with respect to error correction. For a long time, I said partial error correction would be the awkward teenage years of quantum computing, because you have to trade physical qubits for fidelity, right? So you want to do some error correction, but you're not going to be quite to fault tolerance yet, and you're going to have to figure out where to sit in the middle. But now that we're getting there, it seems not so awkward to me, and the reason is that the benefits of error correction, even at the beginning of the curve of implementation, are tremendous. If you're building a quantum hardware platform, you're always pushing for fidelity in your idle state, fidelity in your state preparation and measurement, and most particularly fidelity in the implementation of your gates. And every little bit of fidelity that you gain in your hardware capability is multiplied and amplified by an error correcting code, right? Every bit you push that wall out, you get within threshold for a more capable code that you could run on your system. And so we are shooting for that. We see that as the key enabling technology that will allow us to run useful and deep circuits in a shorter amount of time. And it's just really, you know, you get to be, instead of on maybe a linear scaling curve or even a scaling curve that curves a little bit this way after you've cut down the easy trees in the support infrastructure of your error budget, then you get to be on this trajectory to really low error and really high performance in the circuits. So to me, that's the challenge of the next 5 years, is really getting to good error correction.
Excellent.
So yeah, I do agree that I think many of the modalities are going to continue to be important for at least the next 5 years. I think that there's, you know, given, you know, we share at EeroQ a similar philosophy that any part of the quantum computing stack is sufficiently hard to try to develop. That's what we're essentially a really pure play hardware effort. We partner with on the software side and the algorithm side. Because, you know, we really have to push the hardware side of things. That being said, we also, I mean, the big benefit to, one of the other things about error correction that is really fantastic is if you can, you know, there's a trade-off between number of qubits and fidelity. So if you can make qubits very cheaply and you can make a lot of them, then that also helps a ton. And that's a big part of our philosophy. So while we push the development of all the fidelities and get all those as high as we can, we also can just pump a lot of qubits into the chips. So we have roadmaps that go out to the 10 million kind of qubit level, all on a centimeter scale kind of monolithic chip. But I do think that there's going to be a ton of, I mean, these different platforms are going to be interacting with one another, learning different things from each other. Actually, one of the things that I think is really, while at EeroQ, we really do focus on this monolithic single chip kind of quantum computer as our ultimate goal. Actually, all the things that we've learned how to do come from other quantum computing platforms. So for example, right now we do all of our qubit readout resonator based, which we borrowed from the framework of circuit quantum electrodynamics. Like if that hadn't developed, you know, we'd be like, we wouldn't know how to do it. Like, that is something that we borrowed. There's a lot of similarity to the electron spins, to those electron spins that are in semiconductor materials. So learning about how to design quantum dots and develop spin qubits in that system, we've learned a ton about. And then recently, all the shuttling work, the beautiful shuttling work that the neutral atom people do, actually there's an amazing set of parallels there for, we move our electrons around using just voltages, but the same kind of, you learn a lot about how to do something right from looking at your colleagues. And so I think that's been a big win for at least our technology. I mean, I hope the cross-pollination goes in many directions, but that's been a big part of it.
Exciting. And Lorenzo, you're already working with two modalities, both superconducting based, but annealing and gate based models. So how are you thinking about the strengths of these different technologies within D-Wave, but also in the broader ecosystem?
Well, in general, we think there are some capability that are always going to be better on annealing. For example, optimization. But there's a lot of things that you can't do on annealing. So, for example, I don't know, differential equation or something like that. You know, a gate will always be better. Then there's kind of an in-between. There's a bunch of workloads that could run on both. And then there are some things that, from a practical perspective, just don't make sense to run on neither of those. And that's why GPU and CPUs are always being the picture. We certainly don't think that, oh yeah, quantum will take over the world, just like, you know, GPUs have taken over the world. So it's always going to be a mix of those. So there's definitely going to be an important layer around how you don't want to have every developer worry about all these capabilities. So a software layer that basically knows, okay, this payload is better to use this capacity and so on. Now, within those, we keep on checking everything, every new type of technology out. We still believe at this point that, you know, superconducting is going to be, in the end, the better answer, because primarily we think that once we solve the issue of scaling, and which we think we can, and error correction, just superconducting is just faster. But, you know, we're evaluating every quarter. We go through a whole analysis to figure out we missed something. So we're not enamored, but right now we just see that data. So that's where we're on through that path.
Excellent. Well, thank you for introducing this topic of heterogeneous with hybrid quantum classical GPUs, CPUs, different types of quantum processors. We want to hear from you. If you would pull up your app right now, there's a poll out there. And we want to hear what you think workloads will look like in 2030. I'll give you just a moment to respond, and I can publish the results of that poll. And then we're going to hear from our speakers. And we're going to start with you, Johannes, especially because of your role at the Laboratory for Hybrid Quantum Systems. And what is the heterogeneous landscape going to look like in 2030? All right, let's see what the audience says. Have you had a chance to enter your best guess? There's a multiple choice question there. All right, let's see. We'll publish this poll. We've got 10 answers. There's a tie for the top answer. Either it's moving now. Exciting. The answers are coming in now. Let's see. The top one right now is multimodal quantum clusters running completely separate from HPC. The second hypothesis is fully distributed assets for quantum and classical. And then low numbers of people think that there will be primarily single modality processors with some CPUs and GPUs alongside. Also not very popular answer, HPC supported with tightly coupled quantum accelerators, which is a little bit of a surprise for me. I'm going to share these poll results. But what do you think heterogeneous looks like, Johannes?
Yeah, so like I said, you know, at EeroQ, we're trying to develop everything monolithically on a single chip. Ultimately, we think that you can fit all of that in a single dilution refrigerator, and you don't have to develop a lot of modular interconnects and different parts of the system. You just do everything on a single chip using a scaling technology that humanity took 60 years to invent. However, I do wear a different hat. That's in my academic life at the Michigan State University, where my research group works on. It's called the Laboratory for Hybrid Quantum Systems, and I do really genuinely, you know, while I very firmly placed a bet on one particular technology, these other technologies are going to be. I don't think quantum computing is winner take all, at least in the relatively near term. All of these technologies are going to be successful, and it's going to be to everyone's benefit and a real boon to humanity to try to push forward on all of them, to figure out, you know, what we learn, what what things do we, it's going to be surprising, right? We're going to realize that we can do things, one kind of thing with superconducting that we might not be able to do with a slower system. Or systems that have really high coherence could be beneficial for other things. And in fact, I mean, philosophically, my perspective is, you know, you look at your laptop and it's got a bunch of different stuff in it, none of which really wanted to be a laptop when people started working on it, right? Like the semiconductor physics, the liquid crystal displays, I guess magnetism doesn't really exist except in many hard drives and laptops anymore. But classical computing is quite heterogeneous, and interfacing these different technologies together, I think, it's both an interesting scientific challenge, and there's a lot of benefit to making new technologies, both for computing, but also for like sensing and communications. And so like we spend a lot of time in my research group thinking about how to interface. We work on a variety of different things. We work on color center defects in diamond with some of our collaborators. Some of them are here from Great Lakes Crystal Technology in the MSU engineering department. We work on superconducting qubits. We work on piezoelectric materials that can be interfaced with qubits and make phononic communication channels between these systems. And I think it's really, all of these things are hard to get to work by themselves, but it's hard to get them to work with each other. And there's a lot of opportunity and challenges there, but I think that kind of stuff is worthwhile because you'll realize, you know, everybody who works on their own technology is like really expert in that thing, but then it's really amazing to talk to somebody for a little while from a different technology and you realize all the subtlety and the things that you didn't, like you understand on some superficial level how that system works, but then you gain some deeper insight and you realize like, oh, there's an opportunity here to interface these two things together, or to like put them together. And so we spend a lot of time trying to do that. And I think it's really beneficial and it's going to be needed in building these things.
Thank you. And Kristen or Lorenzo, do you have a view on what the heterogeneous landscape will look like and maybe what the hardest interface challenges are where they're at?
Well, there's several things, right? So I continue to think that transduction is a really hard problem and a problem that hasn't been solved, and that's converting the signals from one quantum computer to something another quantum computer can understand. So if we're really going to do, you know, heterogeneous architectures, to me that's the long pole in the tent. That's the pole I don't know how to solve, but there are people who have been working on this. So there's some scientific infrastructure to build on. Something I have been thinking about for a while is the interaction of quantum with classical computing. You call it HPC, you call it whatever you want. It's going to be a capable classical computer if you're putting it alongside the quantum computer. And the root of this is, you know, we all love quantum computers, right? We're here because we want to see quantum things developed, and we think it's an interesting technology, and we think it's a promising technology. But if you go talk to people who don't come to a conference like this and who have options about the kind of technologies they invest in, they work with, they want to know why. Quantum computers are expensive and complicated, and why are you spending your whole career devoting to the advancement of quantum technology? And you know, then you have to start talking about quantum advantage, and you have to start talking about changing scaling curves, and you have to start talking about addressing problems that you can't with today's classical technology. And it's always a comparison to and a contest with classical computing, right? Quantum advantage, it turns out, is a narrow and special thing, and you have to know exactly where it is, and you have to take advantage of it where it is and leave it be where it's not. And that means that you need to be smart about how you design your algorithms, and you need to be smart about working with this incredible state-of-the-art technology, right? Developing classical computers, yeah, it was hard, but you could show advantage a lot more easily because you were competing with a room full of women with slide rules is how the computations were done at that time. Now we're competing with the entire semiconductor industry, and that's a bigger challenge. I think it's a virtuous cycle for quantum computing. I think it pushes us to be better and to prove ourselves over and over again. But really, we need to be working with that community in order to provide the best computational resources for computing writ large and for ourselves as a scientific community. In the end, when quantum computing really arrives, you're going to know it because probably stop talking about it by and large. It's going to be in the cloud and it's going to be easy. Like chemistry will just be solved and everybody will incorporate it into their algorithms as a resource, and it's just going to come from the same data center. And, you know, that's when we'll have done our job completely. And, but maybe it'll be a little less interesting, but maybe we'll all be a little richer. I don't know.
Thanks, Kristen. How about you, Lorenzo? Do you want to answer this one? Or?
Yeah, well, I'll give you an answer. My perspective is I'm a mechanical engineer. Operational research is my focus. 25 years in one specific industry, which is electronic supply chain. So I've gone through the mainframe era, the mid-range, the personal computer, the mobile devices, and I see this thing always coming around, every technology. So I think, you know, I look at it, what problem are you trying to solve, and then what is the right architecture for that? And then there's different choices. I mean, if you look at the PC era, you look at, you know, a two leading company, the Microsoft Intel path went to one way, and the Apple path went the other way, and you can argue which way is better. So they're all using a lot of standard components, but the mentality was completely different in two companies. So I'm not sure there is a, you know, academics like to say, oh, there is the right answer, and I go, I'm a practical engineer. Well, it depends on what you're trying to achieve. So today, the current state of the art, at least for our perspective, is, you know, we have these quantum computers, a dozen of them that are production purposes. We have a cloud layer that is running on standard AWS, and we have fiber optics between the AWS and all the computers. So the integration is done primarily through the cloud, which is, you know, performance is perfectly fine for a lot of use cases. But if you want to extreme performance, low latency, then it wouldn't be right. So that's what we have now in production. But you're looking at use cases now, we're looking at that people want even better integration. So we did an announcement with the Jülich Computer Center in Germany. They're built the only hexascale computer in the world. It's going to be a top floor in the world. All the other ones in the US. And the whole reason why they bought one of our systems is because they want to tightly couple, you know, a computer they've had already for 3-4 years there, but just for this purpose, 2x to scale, specifically for AI workloads, primarily material simulation second. Because they want to test, is there another tightly coupling that would address for that specific use case? You know, for most optimization problems, we give enough performance that they don't need that. And there are some people that interface directly into the quantum computer, but only research labs are doing that. Nobody else would commercially. So to me, it depends. And I think we need to support all the different modality, you know, because it's just like, you know, in the end, all of us are kind of like an NVIDIA. You know, there are different places where NVIDIA chip are sitting, and we're going to have to support all those to support the different payloads from the end customer and depending on their dynamics. I mean, if you're doing optimization to optimize what is the best way to, you know, utilize your defense assets to shoot down missiles that are coming down, you know, maybe you really care about, you know, millisecond response. So it really depends.
Excellent. And as we were preparing for this panel, I think we would be neglectful not to talk about some of the shared challenges that all of these platforms have in being able to bridge to real applications. And we've, so far in the industry, we've talked a lot about technology readiness levels and all of the challenges of bringing up the technology readiness levels. But there's a lot more to bringing a technology to market than only the technology readiness levels. There's the manufacturing readiness levels. There's the supply chain maturity. We have over 400 companies now in the quantum ecosystem, and really in the early days of emerging supply chain, it can still take an awful long time to get certain key components for building all of these different platforms. Form factor engineering, we're seeing, I think over the last 2 years, we've seen 60 to 80 on-prem systems at least ordered, and varying levels of challenges and actually being able to deploy the systems outside of a research lab. So these are really some challenges in bringing these technologies to market as well. And Kristen, I'd love to start with you in just talking about some of these challenges. What would it really take for quantum systems in general to reach maybe data center level? Maybe that's a big challenge right now, but reliability, how can, you know, what are some of the other really important factors in bringing this technology maturely to market?
Yeah, well, some of the other things that I haven't talked about yet, because of course you need the scaling, of course you need the error correction, but I feel like we don't need to dig into that anymore. You need things to be fundamentally stable. You need things to be fundamentally well engineered. You need things to be fundamentally repeatable, right? So we're working this way today at Atom Computing. We are building commercial systems, and if you're doing an atomic physics experiment, you just take a bunch of optics and you put them on a table as fast as you can figure out how to do it with the highest fidelity result expected, right? And then you take a bunch of data and you do your experiment and you publish a paper, and that's wonderful. You've made progress in the academic field. But the commercial system is a very different beast. So we're engineering all of our subsystems for mechanical stability, for thermal stability, right? We're doing all these complementary analyses to make our computers stable, to make them robust. Of course, we have environmental requirements for the facilities where they sit, but really we're maturing the technology, and we're bringing in existing engineering disciplines to do it. So we're no longer a company that's just full of AMO physicists. Of course, we have lots of AMO physicists, and we're hiring more. If you're graduating, please come talk to me. But they're complemented by a whole core of optics engineers and optomechanical engineers and control systems engineers that are, and these are things that bring a lot of professional discipline to the field. The other thing that comes into it is, in fact, supply chain, right? So particularly as an atomic quantum computing company, we live and die by our lasers and optics, right? All of our control, every single thing that we do with the system is done through optics. So our system is only as reliable and only has as much uptime as the least reliable laser in it. So we work directly with laser companies to mature the technology, to get the cleanliness and the power and the stability requirements that we have for our systems. And this is something else that's gonna snowball and gonna help come along, I think, with the field as it matures. As quantum computers become more capable and more useful, there will be more demand for quantum computers. When there's more demand for quantum computers, I won't say our supply chain pays good mind to us now, but they'll pay a heck of a lot more mind to us when our volume is 100 times increased. And so all of that is we got to keep turning the crank on that as an industry to get to that data center place that we want to be.
Yeah, I think that's really right. I mean, I'm going to tell a similar story, but from the cryogenics side. I mean, when I was a PhD student, everybody, you had every dilution refrigerator in the world was essentially a wet system that you poured liquid into. Every 2 days you were pouring. I often joke around that my PhD, I spent time pouring liquid from one bucket into another. Like that was the vast majority of what I did. And because of the efforts that early companies had made in quantum computing, D-Wave being one of them, Rigetti being another, the whole supply chain just changed. The ability to make dry cryostats that you can just plug into the wall and turn on, that can run for crazy long periods of time without any kind of real maintenance, is incredible. And it's something that has really propelled, it goes hand in hand. It propels the technology forward, but then you have all these new companies that keep popping up that have to be more innovative, because these different, lots of different quantum computing platforms fit into these cryostats, but each one is a little different. And so you have to work with the innovative cryogenic companies to develop new kinds of technologies that go onto those systems. We work with, we try to make our systems as agnostic as possible. So we work with Blue Fours, we work with a very innovative company out of Canada called 0 Point Cryogenics, and we do similar things. We worry about the stability issues, I think, are different for us, but we spend a lot of time worrying about local vibrations. We don't want every system to be in a different vibration environment, so we spend a lot of time building the vibration isolation that we need on any system on the mixing chamber of the fridge, so that you can deploy these systems in the future wherever you want. But those kinds of things are amazing. But it is incredible to me that the supply chains have moved as quickly as they have. But they'll probably move, as you say, you build more of these, the volume goes up. That industry is just going to explode.
And Lorenzo, when we were preparing for this conversation, we talked about supply chain and but we also had a conversation about the ecosystem more broadly, the orchestration layer. How about for D-Wave? Like, what are some of the shared challenges of bringing these technologies together in a useful way?
Yeah, because on the manufacturing side, just because we had it longer and we've had systems in outside of our labs now for 5+ years, that has been quite tightened up. I mean, we have system at USC. Davidson is just going live. I think we're announcing this week. We have a system at ULIC for 3 years and so on. So we have, I would call it, coming from where I come from, very low volume manufacturing capability perfected. You know, long lead times, to me, is like, you know, I'm Italian, born and raised there. It's like, you know, when you buy a Ferrari, it takes a few months to get it. You know, you custom build it. You know, we're kind of in that range. You know, a typical Ferrari is 500 units or so. Yeah, we're not even at that level yet. We're kind of maybe do half a dozen systems a year, but at least it's repetitive, it works, and it turns on, and you know, that's and lots of, from a mechanical engineering, when you open up those things, you go, wow, this is lots of engineering. The cooling thing, for example, trying to figure out generic systems, but then how do you make it so that you don't have to maintain them and they can operate 5 years consistently, because otherwise you can't have 99% uptime. Today, the challenge I think we have there is around how do you increase volume. You know, you go from half a dozen a year to, I'm telling them, listen, we probably need to have at least 100 systems around the world to have redundancy in every little jurisdiction, both commercial and defense and so on. And then they got to think about, okay, how do I scale to that? We're still not at a level, obviously, of, well, we're definitely higher volume with HPCs, but not to the level that, let's say, servers or so on. So then at that point, you know, being a manufacturing guy, when you go through increased volume, then a bunch of things need to happen to change your supply chain, how you manufacture and how you assemble and so on. But I think personally, maybe because of my responsibility, the biggest challenge we have in the industry is not so much on that, because we have a lot of smart people and you can get engineers to solve this, is in my mind, the biggest hurdle of being here for 2 years is on the demand side. You know, the demand side is, does the general world understand which use cases the technology that we're developing can provide meaningful business value, so they want to spend money to get to production? I mean, you know, I came on 2 years ago, and most of the people that were buying time on our systems were quantum people that really wanted to experiment and have, you know, toy problems. The problem with toy problems is you do a proof of technology, it works, and then it dies because it's not tied to a business problem, you know. And you know, I'm trying to build a recurring revenue model. That's what I do for a living. I've done that 5 times. I've been in Silicon Valley. I build go-to-market machines, and to me, doing a proof of technology is, yeah, you get money for it, $200,000, but if it doesn't go to production, it's completely useless. So then you got to have not only the technology works, but you're addressing a problem that somebody's willing to pay for it. And so at that point, you got to understand that if it's something you can do in classical, well, they're never going to go to production because you can do it in classical. Why should I change? So you got to go find those use cases, and it's not just the use case, but the instance of a use case where for that customer, we can deliver a compelling business case. That somebody who doesn't understand anything about technology goes, oh yes, that has a return on investment. That, I think, is the biggest problem we have as an industry, because the general world outside of this room doesn't even know what quantum is. And quite frankly, they shouldn't care. I mean, how many of you really knows what goes on in this thing here? Well, I happen to know because I've done supply chain in this thing so I know exactly who the vendors are and so on. They were all customers of mine in previous life. But, you know, everybody uses one of these. So you got to get to a point where people forget what technology is they're solving a real meaningful problem. And that's a tall order. I mean, right now I'm going after only on the commercial side, Fortune 500. And if you talk to the business people, quantum is not even in the picture yet. Now, once we do pick a good use case and you show them results, and mind-blowing, we can do things in quantum that, you know, instead of taking hours and days, you're down to minutes, and the answer is meaningfully better, meaning there's a tangible ROI on that one. That's, I think, what we need to drive, because if there was tons more demand, I'm sure all our companies can figure out how to build something. Of course, I'm biased. I always think that building the go-to-market is harder than building the technology. But I think that's the big challenges. So that's why events like this are very important to spread the word and get more people that really have a business problems to understand that this capability is available either right now for people like us or shortly by a bunch of other people, and put it to practice. And then you need a talent of people that can do that, that can, the system engineers that understand the problem, understand the technology, and can marry that. That's, I think, is the biggest, I run sales, I also run professional services. I mean, trying to get people that understand, for example, optimization or AI or cryptography, and then help them understand what's possible in quantum and bridge that. I mean, it takes me 4 to 6 months to get somebody to a point that is useful in front of a customer. That, I think, is personally our biggest problem in terms of commercialization.
And Lorenzo, I want to come back to this as our closing topic, really about the go-to-market. But before we get there, I want to talk about one more thing. Actually, error correction. Johannes, I'm going to ask your perspective on this. Kristen, you've talked about error correction and how important that is. Lorenzo, you've talked about one of the reasons for pursuing annealing first was you didn't have to deal with this error correction problem. So Johannes, I'm curious your perspective on this. It's been a very exciting year, starting last December when Google showed the scalability of error correction, and then we've just seen a lot of progress, particularly in this last year. We know that error correction is going to be very important. We've seen that drive for error correction driving a need for this heterogeneous landscape of GPUs and CPUs. We've seen a lot of different techniques, whether it's decoders, parity codes, software level solutions. There's a lot happening in error correction, but just curious from your perspective and how what error correction is going to drive in terms of bridging these systems and that heterogeneous landscape.
I do think it's related to what Lorenzo said also, which is that I think the use case, like the demand side, is in some sense bottlenecked by the fact that the hardware in all of these platforms is great, but it's not there yet. It's not at the level where it's big enough, it's powerful enough to do something that's incredibly meaningful. And once that happens, then the demand is going to be pouring in. And so an error correction is very tied to this, right? I mean, all of the gate-based systems are going to need some level of error correction and some number of physical qubits, depending on the fidelities and the error budget. I think that that's going to be a hard challenge. I mean, like, as you say, there's been great progress. People have shown parts of it to work. Nobody has the ability to do. I mean, one of the things that I always think is an interesting tidbit is, like, if you have a large scale, of order 10 million qubit processor that's running error correction, it's running error correction most of the time. Most of what that machine does is just error correction. It's a little bit of the time it's doing some other computational problem, but most of the time it's doing just error correction. And being able to demonstrate that level is going to be a big challenge. And we take an approach, but it's not all bad news. I made it seem like a little bit of bad news, but there is, Mandy alluded to this a little bit, is that there are these, it's not just the surface code anymore. Like, that's not the only game in town. There's all these new error correcting schemes that people are coming up with, LDPC codes, and there's other levels that some people I would refer to as error mitigation. So you can kind of try to mitigate errors without having to run some kind of, topological motion of the qubits around one another. And that all benefits it. But I think that's a big bottleneck. It's one that we spend a lot of time working on. And it affects scaling, because if you have, depending on the level of error rates that you have on your chip, how you process those in terms of data that you send out of the fridge, or however, in our system it's fridge, that's a big issue for scaling, because you've got to deal with, like, all the information that you kick out. And so there's various schemes that people are developing with this, and us too. And I think it's a big challenge, but I think people are making progress. I mean, that's my perspective.
Making progress, and as we made the point before, it's really one of the key challenges to actually get to commercialization. So let's talk about that for a minute. If you haven't answered the poll on the go-to-market and the challenges, go ahead and answer that, and then we'll also be moving into a Q&A. So if you've got a question or you want to vote for one, go ahead and pull your app up on that. So as we transition to market, I'm going to start with you, Lorenzo, because you are the chief commercialization or the chief revenue officer on the stage here today. But let's see what the audience thinks here about challenges and what would most help the go-to-market aspect. The most popular answers here are open architecture frameworks and some shared interfaces or standards for control for software. The answers that weren't as popular were around shared infrastructure and test beds, cross-disciplinary talent pipelines, and supply chain maturity. For the audience was a little less important. But for Lorenzo, where are your immediate potential customers?
Yeah. Well, just to give you a split, we do about 80% of our businesses with commercial entities, including government for, let's say, DoD or things like that. 20% is research labs and university. Of course, when we sell a system, tends to be much more research labs and university. Interesting enough, the way I would answer that question is actually none of above. I think the problem we have is you're trying to build an ecosystem, okay? So think about it when, Windows came out, or when Apple came up with its, iPhone. Hey, what was the thing that really generated a market around those platforms? There's none of these things that are on that list. Who they are is basically the developer community and the system integration community out there that takes those technology and either build apps as ISVs, independent software vendors, or system integrators that get put in the hands of the end customers. So in my mind, the most critical one, and where we're spending lots of time, is building a network of both system integration and independent software vendors that know how to embed our technology within the framework of a much larger business solution they're providing. And right now, that's, to me, being on the go-to-market side, that's my biggest problem. Because if you try to build a go-to-market organically by yourself, you just can't scale. And we happen to be a public listed company. We have access to lots of money, but still, I can tell you, I've raised over $350 million in VC capital. You just can't do it by yourself. It doesn't matter because it's like having a baby. You can't just put 9 women and do it in a month. It takes 9 months, okay? So you got to rely on other people. And so building the ecosystem of people that can know enough about the technology to embed it into their existing product, new products, and into solution, that I think is the biggest challenge in my perspective.
Okay, great, thank you. Quickly, Johannes, Kristen, do you have any client relationships, go-to-market that are particularly exciting or maybe a surprising collaboration?
Yeah, on the EeroQ side, the people that we talk to most often are folks who are interested in drug discovery. So one of our key advisors is a colleague of mine at MSU, Angela Wilson. Was formerly the president of the American Chemical Society. And that's one of the use cases that we really find particularly meaningful, partly because there's some, finding where that advantage line is for gate-based systems is a moving target. You talk to the most optimistic people and they think, with variational eigensolving, maybe you have 1,000 noisy qubits, you're going to be in good shape. Maybe they're right. Maybe you need 10 million qubits that are fully error corrected to really be able to do something meaningful. And so trying to understand where those boundaries are, and as Lorenzo says, it's tricky because the folks, you don't want to tell them about a technology. You want to figure out how you're going to solve their problem. Mm-hmm. And so a lot of our conversations evolve in that fashion.
Excellent.
So we engage pretty broadly, and that's on purpose, right? So we have certain things that we think are first in line to quantum advantage because we can prove they're going to work, right? And that's materials and chemistry. You can prove that there's quantum advantage there. You can prove why. You can do the math. You can figure out what you got to expect and what kind of error correction you got to do and how long it's going to take. And that's really valuable because it sets the target for us on what kind of a quantum computer is going to be useful, right? When are you going to get there? But we still need to, we don't draw the line there. We engage with all kinds of disciplines. In a former job that I had, I was a major defense contractor, and I thought this was important too. I used to like lure in domain experts with quantum computer access. So you want to come work on the hottest, newest thing going, because we need to know what you know about your problem and how it's solved classically, because quantum advantage is narrow and elusive and ever changing. As you know, anytime you put a problem on the quantum computer, the classical computing community instantly gets more interested in it, and all of a sudden you've got a bunch of better solutions. And that's because most solutions that we have with classical computers, even those that are heavily used by industry, are not proven to be optimal. They're just algorithms that we found that work well enough for our purposes, and we don't, then we use them, then we're done. The problem is solved. So you gotta. This is why I think we need to cast a broader net for quantum applications. Yes, the provable use cases are critically important, but there's a lot we do with computers that we don't prove out, much to the chagrin of computer scientists everywhere. And those things are going to be important for quantum computers too. So we need to allow the user community to bring their good ideas. It's not all going to be invented by us who are making quantum computers.
Okay, and we want to make sure we get to a couple audience questions. I'll start with one here that's popular. This is a lightning round, just a quick phrase, okay? Could you share one niche hardware area in quantum where you wish you had more time, R&D capability, or funding to explore? Quick round.
Do we have an order?
What's that?
Do you want us to go in order?
It doesn't matter. Whoever's
In
ready.
order.
And you don't have to answer if you...
Yeah, so with EeroQ, I'm happy with what we're doing. I think we know what we need to do. I think we're doing it. But on the academic side, I mean, if one niche thing that I think would be fun to spend more time on is we think a lot about transduction. I do think that's a big problem. I mean, that's a real, if anybody
Excellent.
if you're a young
Transduction.
person, focus on transduction.
Transduction. All right. Any other quick thoughts?
Photonic integrated circuits.
Ooh,
They're
thanks.
really great for telecoms. They're not really great for visible light. We would love them to be great for visible light, but it takes a lot of money and a lot of development to do. So fascinating, underexplored.
All right.
Well, I'm more software side, but the intersection of quantum and AI workloads, I think it's been unlocked, and we kind of have to do that. Otherwise, we're going to build up a bunch of nuclear power stations. So anybody who can understand AI workloads and understand any form of quantum, please help us out.
All right. And I think we have one quick live question.
Yes, thank you so much for the talk today. But in my industry, I work as a data scientist in the transportation infrastructure and urban planning industry. So almost completely unrelated to what you do here. We are trying to adopt AI, machine learning, optimization problems for our civil citizens across cities, states. So my question really comes down to, in our sectors, we don't even think of quantum computing or what problems it can solve. I myself have a background in CFD myself. I see some areas where it could fit, but I want to kind of bring it to the business aspect, because the first question my VP or my CEO is going to ask me, what is the value add of quantum computing if we were going to implement this here, or why, right? It always comes down to, in the business world, what's the value add of this technology? So for early adopters or people who are trying to figure out where we can fit it, what's your recommendation to kind of bring this conversation, bring you into this space to the executives and our clients? Because in my business, if the client is not paying for it, we're not going to do it, right? That's how
Excellent.
the CEO
Thank
looks
you.
at it.
Advice for early adopters.
Well, I tend to lean to any problems, optimization problems, or even AI problems that takes you hours and days to compute. And using classical computing, you can't model the whole thing because you get the limit. You would like to model 10x, let's say, the number of variable and constraints. That's the one I would start looking to see if that kind of problem in your instance is a good fit for the technology. And so if you could go from hours to minutes and improve the answer by, I don't know, 15, 30%, would that be useful for the business? That's kind of my general parameters, and evaluate maybe a half a dozen or a dozen of those, and then prioritize which one to start with.
Any other quick advice for early adopter?
I'd ask myself what kind of data needs to go into the quantum computer. How much is it? Data I/O can kill a quantum advantage pretty quick. Is it maybe worth it because the transformation of putting the data into a quantum space will cause different correlations, will cause, transformations are a powerful tool. Is that something you can use? Are transformations that are fast in the quantum space, further operations on that data fast enough to provide you a narrow quantum advantage after you get your data into the machine? Or can you think of something that's really a hard computational nut that doesn't require a lot of data to be fed into the machine? And can you map that somehow to linear algebra, because quantum physics is made of linear algebra? And if you can make that native mapping, then you're on an efficient track.
Okay.
I'll just
15
add
seconds.
one brief thing. I think both of those are really great answers, especially about optimization. Another thing that is useful, I mean, there is going to be a back and forth need. So the users are going to, if a company has some use cases that they're thinking about trying out with quantum, talk to the quantum companies and see what you kind of have to start. It has to go both ways on some level. To both, it advances the technology, but it also figures out whether it actually does benefit you. And if it doesn't, then you learn that, and there's some amount of that. But if it does really benefit you and you don't do that, then you miss out. And that's nobody wants to become Kodak.
All right, excellent. So final words from our panelists in one phrase or one sentence. We come back here in 5 years. What is it most that you hope we have bridged at that point, either technically, business-wise, organizationally? Kristen, we'll start with you.
Error correction.
Excellent.
Yeah, I think error correction is important. For our particular technology, I think we spend a lot of time talking to semiconductor foundries and developing better R&D and new processes in those foundries to meet the new technological demands of quantum, I think is really important, and one thing that is evolving, but I'd like to see that evolve even faster.
Excellent. Lorenzo?
5 years from now, I would love to see companies and governments advertising quantum-powered applications, just like they've done mobile apps before that. And think about it, 20 years ago when people put on the first website. Same idea, quantum-powered apps.
Excellent. Well, as you leave today, invite you to come and talk to any of our panelists who have so generously shared their time and ideas. Also glad to talk with you, TreQ. We're doing open architecture, quantum systems engineering, quite relevant for this bridging topic. And please join me in thanking our panelists.